Before I start my presentation, I would like to acknowledge all the co-authors and the partners that worked in this project. So I represent the Swedish Geotechnical Institute, which is shortened SGI. And then we had a landfill owner called NSR. This is a landfill owner that has a landfill in the southern part of Sweden, and it's also a recycling company. And then we have SLU, which is the Swedish University of Agriculture Science. And then we have another Swedish university called Örebro University. And then we have partners also from KTH, which is the Royal Institute of Technology in Sweden. And this project was funded by a research funding platform called Resource. And behind Resource is 3 organizations. It's Formas, Vinnova, and the Swedish Energy Agency. So these funders provided approximately half of the money for this project, and then the other partners here below joined in with the rest of the money. And the name of our project is Biochar, from organic waste to resource for treatment of contaminated soil. Oh, I'm trying to switch slide, but nothing is happening. Okay.
Yes, it's working.
Now it's working. Good. To give you some background before I go into results and conclusions, like Europe, Sweden has very much contaminated sites, and the most common remediation technique is still dig and dump. So we excavate a lot of soil and put it on our landfills. And we also need large volumes of uncontaminated or juvenile soils to backfill the excavated soil at these areas. And as you all know, soil is a highly valuable natural resource that we need to take care of. And therefore, we really need to find sustainable remediation options, that is dig and dump technique. And biochar, we wanted to investigate if biochar could be such an option. And for you who are not familiar with biochar, it's like charcoal, but it has to be produced in a sustainable way to be able to call it biochar. And one way to produce this sustainable is to use organic waste as the feedstock, and then you burn it through pyrolysis. And this means that you don't add any oxygen to the process, and then you get this charcoal, which you can see here on the picture. And biochar or charcoal has been known as a soil amendment material for more than several thousands of years. You could actually find charcoal in the soil of Amazonas that is more than up to at least 7,000 years old. And what you also can see is that the biomass production above a soil that has been treated with biochar is better. You have an increased biomass production compared to soil that has not been treated with biochar. So the biochar can act as a soil amendment and increase the fertility of the soil. And this is done by several effects from the biochar. And one is that the biochar increased the water holding capacity of the soil. It also makes the soil better to hold nutrients, so you could prevent fast leaching of nutrients, like nitrogen, for example. The biochar could also increase the pH of the soil, and it counteracts the compaction of the soil. And all these together could increase the fertility of the soil. Another good thing with biochar is that it could act as a carbon sink, so it's a very environmental friendly product. And this is done by when the biomass that you use for production to biochar, when it is grown, it captures carbon from the atmosphere, and the carbon in the biochar is actually in a more stable form compared to organic matter used in a for example, compost, amendment material. So when you put it back into the soil, it acts as a carbon sink. And the good thing, at least in Sweden, is when you produce the biochar, you could actually use the excess of heat that comes from the production and heat up houses, for example, so you could replace fossil energy. And to close the loop here, the biochar, when it acts as a fertilizer or a soil amendment in the soil, the biomass could be higher on the area, and the trees or what you grow here could actually capture more carbon from the atmosphere. So in Sweden, biochar has been used as a soil amendment already, for example, for tree plantations in urban areas, as you can see here on the picture to the right. But we have also tried it in soccer fields and in green walls and roofs because it's a very light material. But in our project, we wanted to test if it could also be used as a remediation technique to treat contaminated soil. So our main aim was to use biochar that had been produced from organic waste to stabilize contaminants in the soil. And by doing that, we wanted to improve soil quality in order to reduce both environmental risks and also reduce the amount of waste that could be produced. And it has been a 2-year-long project, but we have been able to find additional funding. So the project is still ongoing, actually. And here you can see the project structure. We had one work package that were dealing with production of biochar. They investigated what type of feedstock that you need and what type of temperature that is needed to produce biochar that is suitable for different types of contaminants. And I'm sorry, but I don't have the time today to present results from that work package. But if you have questions, feel free to ask afterwards. So today I'm going to focus on the lab and the field study that we made. And I'm going to give you some short information about and results from another work package that dealt with policy and legislation regarding how a treated soil could be reused. And then we also performed an environmental analysis for the whole process. And we performed an LCA, a life cycle assessment, and I will give you the results from that as well. But I will start with our field study. And the goal of the field study was to answer the following questions. When is a treatment with biochar suitable? What type of soils can be treated? And how much biochar do we need to put into the soil to see an effect? And we had several specific objectives. We wanted to investigate the effect of biochar both on ecological key parameters, but we also wanted to see the effects of the actual contamination situation. So we investigated effects on leaching, bioavailability, and ecotoxicity. And at the time when we wanted to start our field study, there were no soil, we couldn't find a soil that had all the contaminants that we wanted to study. So we had to use soils from 2 different sites and mix them to get one soil. So the first site was a gaswork site, and it was heavily contaminated with polycyclic aromatic hydrocarbons. And then we used another soil coming from an excavated harbor area, and it contained metals like lead, zinc, copper, and mercury. And we mixed these two piles together, and then we added 1% of organic matter coming from garden compost. And this was our reference soil, our contaminated soil, and this soil was then divided into 9 different piles, as you can see here. And to try to study different type of soils, we added peat to in a 1.5% to 3 of these piles. And then we added a little bit more peat, up to 3% in these piles here. And then we studied addition of 0, 3, and 6 to these soils. 0, 3, and 6% of biochar in weight percentage. And everything was done in triplicates, and we filled the mixed soils into cultivation beds, as you can see on the picture here. And on top of that, we put seeds of an English ryegrass. And after 1 growth season, we analyzed uptake to this grass, and we looked at leaching and several more things. I have a picture of that as well. But before, some photographs of the mixing. So here you can see the biochar coming in big packs like this. And here we are doing the mixing. So here is the biochar, and here's the soil. Here's a close-up of the biochar, and here's a close-up of the peat. And like I said, after 1 growth season, we did the following analysis, as you can see here. So in the grass, we looked at the chlorophyll with a SBAD meter. We investigated the production of grass, the biomass production, by cutting and weighing the grass. We looked at uptake of pHs, metals, and nutrients in the grass. And we took soil samples, as you can see here. Here is a hole where we have dug up some soil. And in the soil, we analyzed nutrients and cations and total organic carbon, total inorganic carbon, pH, texture, water holding capacity, and of course, metals and pHs. But we also investigated characterization of microorganisms responsible for the nitrogen cycling, and some or soil samples from all these treatments were also tested in batch test to see how much metals and pHs they were leaching out. And we also performed ecotoxicity tests by adding earthworms and looked at acute toxicity and reproduction of earthworms. And those earthworms were then also analyzed to see how much metals and pHs they have taken up. So if we move to the results, here you can see the contamination levels in the soil, both the untreated and the treated soil. So you will have increased amounts of biochar on the x-axis. And the colors is for the different soils. So white color is with no additional peat. That is the soil with a low organic content. And then green, light green is with adding 1.5% of peat, and dark is 3% of peat. And as you can see, we had high amounts of high concentrations of copper, lead, and mercury and zinc. The red lines here is the Swedish guideline values for less sensitive land use, and the yellow line is our guideline value for sensitive land use of contaminated land. So we were above these guidelines, 1 or 2 of these guidelines for all of these contaminants. And if we go to results from the biomass production, we had expected to have an increased production with the addition of biochar, but we received the opposite pattern, as you can see in this graph here. So on the y-axis, you have the biomass in kilogram per square meter, and it goes down when we add biochar. And this was because the availability of nitrogen in the soil water were reduced. For this treatment, we had chosen a biochar that has a really good absorption affinity for both organic contaminants and metals. So this also resulted in a very good absorption of nitrogen. And low availability of nitrogen also resulted in lower concentration of chlorophyll in the grass and the less biomass production. And this is only after one growth season. And now when we are doing a follow-up study, we can see that it has been evened out. So it now, 2 years later, it looks like the biochar is again releasing nitrogen. So if we move on to the results of the leaching experiments, here you have the results of the leaching of pHs, and the concentration of all the 16 pHs that we investigated radically decreased. So you can see here a very sharp trend with more biochar in the soil. And if we look at the table here, here is the leaching of the pHs from the treated soil in relation to the untreated soil. So if we have no additional biochar, 100% is leaching out. But already after 3%, additional 3%, the leaching is reduced down to 3, 4, or 7%. And you will get the highest reduction if you treat a soil that has a low amount of organic matter. So if you look here at the number 2 and number 3 soil where we have an additional peat, the reduction is not so drastically like in the first case here, but still it's a very good reduction. And we received the same pattern for metals, but not equally as good as for the pHs. Here we were able to reduce down to 35%, for example, when we add 3% of biochar, and down to 22% when adding 6%. But again, the same pattern. When we are trying to treat a soil that has a higher amount of organic matter, you get a less reduction. When we looked at the uptake in the grass and the earthworm, we saw a reduced uptake of pHs, copper and zinc, but we couldn't see any difference for lead, and we were not even able to detect mercury because we were below detection levels. In the earthworm, we saw a reduced uptake of all the contaminants, but again, we were not able to detect mercury because it was below the limit of detection. So we draw the conclusion that it's a better environment for earthworms here, and we also saw effects in our ecotoxicity test. We didn't see any acute toxicity in any of the cases, not even in the highly contaminated reference soil. But we had a suppressed reproduction, almost no reproduction of earthworms as well at all in the heavily contaminated soil. But when after adding biochar or peat, the earthworm could start to reproduce. So I should say also that the peat had a bigger positive effect than the biochar. And we also saw that it was better to add just 3% of the biochar compared to 6% of the biochar in case of in terms of reproduction. So conclusions from a field study is that 3% of biochar is enough to see a sufficient drastically reduced solubility of pHs and also a reduced leaching of heavy metals. But the effect is very site and biochar specific. So you will get the greatest positive treatment effects in relative terms in soil that has from the beginning a low soil quality. And by low soil quality, I mean low content of organic material, but also a low clay content and a pH less than 7. I think I have time to give you some results also from our environmental system analysis. So this is what we are looking at here. In this LCA, we compared the alternative to use the dig and dump technique and excavate the soil and put it on the landfill. And this alternative was then compared to off-site and on-site treatment with biochar. And our LCA showed that the biochar treatment has a significantly lower environmental impact compared to traditionally landfilling. And treatment both on-site as well as off-site resulted in negative CO2 emissions under prevailing Swedish conditions. So in the example here, remediation of 12,000 cubic meters of contaminated soil would result in 1 million kilograms CO2 if it is the dig and dump technique. But instead, if we use biochar, we could reduce the emissions and get a negative emission even of almost above 2 million kilograms of CO2 equivalents. In the environmental system analysis, we also did a substance flow analysis, and this is what you see here below. And we used the results from the field trial here, and then we simulated leaching over 100 years. And as you can see, we have a reduction in concentration of pHs when we compare the landfilling options with the treatment with biochar. The same for copper, but for contaminants that could act as anions in soil, like arsenic, chromium, molybdenum, vanadium, there could even be an increase when you use biochar. And this is probably because some biochars could increase the pH in the soil. And that increased pH can make those compounds more mobile. So you have to be aware of the contaminant situation. And if you have contaminants that could act as anions, maybe biochar is not a good option. Just very short, some results from our work package that dealt with legislation regarding use of biochar. We saw that existing Swedish and international law regarding waste and remediation of contaminated sites are very complex. And regarding biochar as a treatment technology, the legal conditions for its use are not very clear, in Sweden at least. And this creates uncertainty among the users. They probably won't dare to try the technique. And we are also lacking case law in Sweden. And so what we could do in our project was that we started to identify a set of critical questions that users of biochar can take a stand on in order to correctly navigate through current Swedish environmental regulations. And these questions can also facilitate for regulatory authorities in order that they could give guidance on what documentation the regulatory authorities need to request. We have also identified future challenges The first one is that we really need to provide guidance in the future to increase safe recycling of soil. And we also think that more good example is needed. If we dare to try this technology, more could follow. And if before we don't, we need to do this when we're trying this new technology, we need to do this in combination with control programs. So you could abort if you can't guarantee the safety, if you see that the risks is increasing. But still, we think it's important that you try this technology, so we have lots of good examples. And what we are trying to do now is to verify the stability of the treatment. So we will continue our field study and investigate long terms to see that the leaching stays on a low concentration, both for these pHs and the metals. And in the upcoming years, we will also look at effects on soil functions and toxicity. So this project has provided a lot of reports, but I'm sorry, most of them are still in Swedish, but we are trying to do our produce our papers. So it will next year, these 3 papers will come, but we still have some papers in English if you're interested to read more about it. So thank you very much for listening, and I would be very happy to take your questions.
Thank you very much, Anya, for your nice presentation, very clear. I've seen that there were some questions in the chat, so I will go through them in the order, I would say. There is a question about the extent of soil's pH increase by adding biochar. So do you have an idea of the range of it, the extent of soil pH increase?
Sorry, could you please repeat or rephrase?
Yeah, so when you add biochar, there is an increase in the pH.
In pH, okay, yes, it is.
Okay. What is the extent of that increase?
Yes, the specific biochar we used didn't have any significant effect on pH in our case. We couldn't see that, but there are biochars that contains lots of ash, and ash is could increase the pH half a unit, I would say, or something like that. But it's also an effect that is not, it will not stay, the high pH will not stay for several years in the soil, because these ashes will be washed out, and then the pH will drop down again, I would say.
Okay, and does it depend then on the type of biochar?
Yes, it does, very much, and very much on the process, how the biochar was produced, what time of feedstock and what time of temperature were used.
Because you used the wood waste, right?
Yes, exactly, and we burned it at a very high temperature to get a stable biochar.
Okay, thank you. There is also a question about the mixture percentage. Are they given by dry mass or wet mass?
Dry mass and weight percentage.
Okay. And there is another question about what would the percentage of biochar addition of 3 and 6% be based on? Why did you choose 3 and 6%?
We did a lab study, and we also did a literature search, and we came to the conclusion that some other studies had seen toxic effects at higher amounts than 6. It was a study where they used 5% and 10%, and at 10% they saw some toxicity effects on the soil living organisms. So this is why we wanted to test it below that amount.
Okay. A question from a guest. We don't know exactly who he is, but who she is, maybe. It's referring to the lowering of biomass production because of the storage of nitrogen. And then after 2 years, you mentioned that the biomass production became normal again. And the question is, does biochar store pH metal on the long run, or will they be released after a while as well? So that's
This is what we actually need to test now. So this is why we have received extra funding, and we will continue to follow up bleaching at least for 5 years to see if the level stays as low as initially received. And we have been able to do sampling now for 3 growth seasons already, and they haven't increased. The concentration in the leachate in the soil water has not increased, so it still stays low.
Yeah, that's the big issue for
yeah, it is.
of the system. You get some congratulations from Miguel Isquier, and he's just asking if the biochar has to be activated in any way.
No, we did not. It's not activated, but we used a very high temperature for producing it. So it has common characteristics like activated carbon. It has a very high porosity and lots of surfaces.
Okay. There is a question also about the initial properties of soils. So like pH, organic matter, lead content, for instance. Given those characteristics, what reasons could explain the better results of biochar without peat addition?
The soil had a rather high content of clay already, and also a rather high pH value. So it was already from the beginning kind of a good adsorbent for metals, and not so much for pHs, but it was an aged contaminated site that we used, and the availability of the pHs were not so high due to the aging processes that had already been going on in that soil. So if we had started with another type of soil that had lower soil quality or fresher contaminants, then we would maybe even have seen a better effect of the treatment, I would answer.
Also a question about the temperature of biochar production. Going back to the process of
yes. What we used, was that the question?
So what was the temperature?
850 degrees Celsius degrees.
Okay. And you saw that in your life cycle analysis, still the biochar production was better than landfilling.
Yes, of course. Yes,
despite,
definitely.
Okay.
But I must remember to say that in Sweden we use electricity for production, and the electricity is a non-fossil, is a fossil-free production, because we use nuclear power and water to get electricity in Sweden, most of the cases.
Okay, so another source of energy would have maybe changed the pattern of SCA.
Definitely, yes.
I have also a question about the legislation part a bit more.
Yeah.
You have shown the different levels and thresholds that are used in Sweden, and you show that the ending soil was still sometimes going over such thresholds. So that means what kind of use can you do with such soil then? Do you need to target some?
The problem is that we still do risk assessment based on total amounts in Sweden, and I think we need to change that to go to a risk perspective instead. And if we had guideline values that is set on water quality, then it would be easier to get an acceptance for this kind of treatment. So yeah, actually, to get acceptance here, it's very important that you could do a really good risk assessment and really prove that the risks is going down, because you will not be able to reduce the actual amounts of contaminants in the soil. It will still have high amounts because the contaminants will adsorb to the biochar and be there.
Mm-hmm. So that means that you are more targeting the water protection than above ground, I would say, use for food or feed, of course.
And then by the help of ecotoxicity test, prove that the soil quality is improved, that there are no risks for the soil living organisms. To do the environmental risk assessment.
And yeah, okay, that raises some reflection in my mind, but I see that there is another comment in the discussion. Experiments show that higher temperatures with production also increase the pH content of biochar. Did you experience similar results? So increase of the pH with the higher temperature production.
I don't think that we studied enough samples to see that effect, that the PAH is increased. Was that the question? Or pH?
Yeah.
PAHs.
PAHs, yes. Content of biochar. In the biochar.
I understand. We had high amounts of low molecular pHs, but we couldn't see a trend with increased temperature because we didn't study so many samples. But the pHs in the biochar were very highly adsorbed to the biochar. They were non-mobile. We couldn't see any release of them to the water. So the biochar were actually able to capture more pHs. So it's a very good adsorbent.
Okay, both intrinsically and the one from the contaminated soil, actually. So both types of pH were absorbed in the final mixture. Okay. I think I don't see any more questions, and that the time is
out. Yeah.
is up also. So I would like really to thank you, Anja, for your nice project and presentation, and your colleagues, of course. You were not alone behind it, and also thanks all the participants for their question and interest. And yeah, I would say see you next time to a next coffee break.